third video on the puzzle of the Pictish stones. I've been exploring the idea that the pictograms are emblems of learning, that they show the degree of apprenticeship of Pictish stonemasons, and that they indicate a level of geometric knowledge. The first looked at the V-rod and crescent and its connection to Hippocrates' quadrature of the lune, and the second looked at the Z-rod and double disc and its connection to internal and external common tangent lines for two equal circles. However, the more complex type of Z-rod and double disc, which I call type 2, is curious in that, on the one hand, the curved dumbbell handle shape seems to confirm it was all about common tangents, but on the other hand, in these type 2 Z-rod and double disc figures, the Z-rod no longer touches the double discs, and that's the whole point of tangents. So I suspected that in the type 2 version, the Z-rod had come to stand for something else. Initially, I thought that maybe the original idea had simply become corrupted by copyists not knowing the significance of what they were copying. But there was something that bugged me about this. I didn't like the idea that it was the more complex versions that had become geometrically corrupt. This seemed the wrong way round. But I later came to realise there was something a lot more elegant and sophisticated going on. The big clue came from noticing that the type 2s are often accompanied by a handheld mirror symbol. The thought that popped into my head was that the mirror might be there to indicate reflection in the geometric sense. And soon after that came the thought that since the Z-rod is made to look like an arrow and thus implies direction of movement, it therefore looks like the path of a ray of light reflected first in one mirror, the zig, and then another, the zag. I then realised that the way that the Type 2 Z-rod and double disc differs from the simpler Type 1 matches exactly with the changes that would be needed to make it a proper depiction of a reflected ray with correct angles, showing an awareness of Euclid's formula for reflection. The formula is as follows: the angle of incidence equals the angle of reflection. Let's first go back to the type of construction we looked at in the previous video. So we'll start with the common internal tangent line for the two equal circles. Now let's draw in lines parallel to one of those internal tangent lines, one that starts from the centre of one of the circles and one that starts from the centre of the other. A circle that's centred on the midpoint of the figure with the circumference going through the centres of the two circles is part of the alternative method for constructing internal tangents, which we don't need to go into here. But what we can notice is that where it crosses those parallel lines that we created to be parallel to one of the internal tangents, we have now created a rectangle on a slant. Let's take a look at the angles that are formed by this rectangle. If we have a rectangle slanted like this, and these are three parallel lines, then we know that this angle here is equal to this angle here, because these two lines are parallel, making these alternate angles. But we also know that this line is parallel to this line, and this is a line running across those two lines. So again, this and this are also alternate angles in that sense. So this is also alpha. So in other words, this and this are equal. In other words, this line bisects this angle into two halves. If we were to say that this is the surface of a mirror and this is the surface of a mirror, then we can say that if we have an image or light coming in from here, then when it strikes this reflective surface, because as Euclid also tells us, the angle of incidence is equal to the angle of reflection, then we know that when it reflects off the surface, it will be travelling along this line here. And then it's going to come to this mirror here. So when it hits this surface, the image is going to come along this line here. And that is what allows this to become a diagram of reflection. It fascinated me to think that the Z-rod and double disc might be demonstrating all these things. Firstly, a knowledge of how Euclid's ideas on angles relating to parallel lines can be used for practical deductive purposes, and also a demonstration of some elementary knowledge about construction techniques for internal common tangent lines, external common tangent lines, and some basic tangential circles. But also, perhaps most intriguingly of all, knowledge of Euclid's formula for reflection. This last one was perhaps the most interesting, because Euclid's book on reflection is not thought to have been one of the ones that was present in early medieval Britain. What exactly was going on here? That's a question that we'll look to answer in the fourth and possibly final video in this series.